Okay, so welcome everyone. So thank you for joining us for the RecSys 2020 session on reward applications. So my name is Yongfeng and I'm your chair of this session. So just a little housekeeping before we get started. If you have any questions for a particular presentation, so please hop on to the Hua agenda entry for that presentation. If you are on the desktop app, then the live video streaming will keep playing on the floating window, so you don't miss anything. So we have a tight schedule, but I encourage you to follow up with speakers and continue the discussion after the session on Hua. Without further ado, so let's get started. Our first speaker will be Xu He from Nanyang Technological University. So Xu, can you share your screen and begin your presentation? Thank you. You are muted. Can you unmute yourself?
Okay, thank you.
Yes.
Wait a moment.
Yeah.
Can you see it?
Yes, we can see it. Yeah.
Okay.
You can start.
Okay, thank you. Okay, hello everyone. I'd like to talk about my paper, learning to collaborate in multimodal recommendation via multi-agent reinforcement learning without communication. This paper is a joint work of Nanyang Technological University and Alibaba Group. We first introduce the setting and motivation of our work. In many e-commerce platforms, there are multiple modules on one page to recommend items with predefined properties. For example, items with 0% installment and special discounts. Different teams are in charge of different modules, and their objectives are the same, to get more clicks by user. Different agents with the same objective and individual optimization usually lead to competition and suboptimal global policy for the e-commerce platform. For example, there is a repetition of items and categories in these two figures. The interactions between users and the platform is a sequential decision problem. Users can go to module pages and item detail pages or refresh the entrance page to obtain other recommended commodities. So we use multi-agent Markov decision process to model interactions. In MDP, modules are agents and users are environment. Agent ranks items based on users' features and obtain clicks as reward. Users' features will change according to their behavior. The challenges in this process are that we need to mitigate competition between modules without communication, since modules need to recommend items simultaneously within a very short period. So many works apply reinforcement learning to recommend the system domain. Their contributions can be divided into three kinds. Some of them consider different kinds of rewards, like return time. Some propose methods for the structure of web page. For instance, take the whole page as input and consider advertising. Others focus on the huge space of commodities. Some clustering methods are used in such work. Only two papers apply multi-agent reinforcement learning to recommend the system. They consider the sequential pages controlled by different agents, and that's after users leave the first page, the first agent can send messages to the second one, and the second agent can act as based on both user feature and the message. The difference is that we consider the agents that acts simultaneously without communication. So our idea is inspired from correlated equivalence, which is a concept from game theory. A simple example is intersection and the traffic light. If there are two cars that want to go through the intersection, both of them can choose to go or stop. If both of them choose to go, they would crash and pay $100 to repair the car. If they both choose to stop, they cost 1 minute to wait. But because of the huge loss of the crash, 2 cars are prone to choose stop according to game theory. Actually, it's about 99% to choose stop. However, this is not the optimal solution for the traffic or for the intersection. So the best solution is to use a traffic light to tell them to go alternately. So in our paper, we introduce a signal network to send signals to different agents to maximize the overall reward. Additionally, an interface regularized version is proposed to promote exploration. We also implement experiments based on dataset from Taobao. So the architecture of our method is shown in the figure. Our method is based on actor-critic algorithm, which is popular in reinforcement learning. There are 3 components, the signal network, actor, and critic. The input of the signal network is a user feature, and the output are signals to promote cooperation. The actor is to rank items given a user feature and signal. And the critic aims at estimate the cumulative reward obtained by the output of actor and provide gradient to actor. So here is a detail of these components. Each of them includes a state embedding module to get the embedding of different users. The features of users can be divided into 2 types. Static features include gender, age, and other fixed properties. The sequential feature consists of features of historical clicked item by this user. We use attention mechanism to get the embedding of the sequential feature by learning the weight of historical items. For the ranking part, our actor output vector as the width of elements in item feature. We use an embedding layer to get item feature and then use a weighted sum of action and the feature as score of item. For each agent, we apply a soft actor critic algorithm to update parameters, which adds an interface of policy pi to encourage exploration. Each agent aims at maximize their own reward. For the signal network, the objective is to maximize the overall reward. However, the policies of agents are changing over time. We propose to use interface regularized version of update to explore how to choose the best signals. By this way, our algorithm explore more before convergence, which is shown in this figure. The shaded range shows the best and worst performance in multiple ranks. Algorithm without the interface term doesn't tend to explore drawing training. So in our experiments, we use NDCG and precision as metrics. We use 14-day records as training data and 3-day records as testing data. In each record, there are 10 candidate items for each module. The task is to rank these 10 candidates, and the clicked items should be ranked higher in each module. We use supervised learning method, reinforcement learning method as baselines, and also 2 methods for ablation study, which is our algorithm without attention and interface respectively. So here is a result of the offline experiment. We classify baselines considering their properties. So there are 2 single agent methods, some multi-agent reinforcement learning method, and then we apply soft update for this multi-agent reinforcement learning method, and then our method with some ablation study. Then due to the huge cost and the risk caused by deploying different algorithms to the real-world scenario, we build a simulated online environment. A simulator is used to simulating users' interactions. Given the recommended items of 2 modules, the simulator provides the CTRs of this item. By this way, the interaction of modules is considered. In this setting, we store 2,000 candidate items for each module, and each agent recommends 3 items. We train our model by 60,000 steps and get the results by 10 runs. So the bar graph shows the results of all the algorithms. The results in the red box are the performance of our algorithms. I mean, including the ablation study. Again, we illustrate that the interface term promote exploration before convergence. So in conclusion, we first model the multi-module recommendation as multi-agent reinforcement learning problem. We then design a signal network to maximize the overall reward. Thirdly, we propose an interface regularized version to coordinate agents exploration. Additionally, we implement online and offline experiments based on dataset from Taobao. So that's all. Thank you.
Okay, thank you, Xu. We have a question from the audiences. Could you explain how the signal network combines each agent goal into an overall goal?
Okay. Let me back to this figure. So you can see the signal network will send a signal to each actor, and the signal is used as the input of actor. Since the objective of each agent is to maximize their own reward, and the objective of the signal at the network is to maximize the overall reward. So the gradient of the signal network is actually the sum of each agent gradient. So in practice, the gradient will come back from actor to the signal network for each agent. So in this way, the signal network can maximize the overall reward.
Okay. Okay, thank you. Yet another question, still from the audience, is how did you tackle exploration while deploying a model online?
Okay. As I mentioned in this figure, we use this interface term to coordinate exploration of each actors. The interface term is aimed at to encourage the exploration of the signal network, since the policies of each agent are changing over time. By adding the interface term, you can see that in this figure, the variance of our algorithm during training is very large. So it means that agents are more like to exploration during the training, and then conversion to the optimal solution. Yeah, thanks.
Okay, thank you. So I have a question that I'm interested in for the user simulation part. So how did you, can you talk more about how did you simulate the user behaviors when in the online experimental setting? Yeah.
Okay. So in this, in our simulator, the input of the simulator is this page is an example. So multiple modules recommend some items, and we use all these items as the input of the of our simulator, and also we use the user feature as input. So in this way, our simulator can consider the who page as the input, and consider the interactions between different modules. It means that if the recommended items of one module changed, then another module will be affected by this change. Because our simulator takes the whole page as the input, the situation I said before can be considered in this simulator.
Okay. So you are doing So you are doing interventional experiments using these pages. Okay.
Yeah. Thank you.
I think the last question, we have to make it very brief. Can you share more about RL deployment to production?
Okay. In our paper, we actually use simulated environment because of the huge cost and risk caused by deploying different algorithm to the real world scenario. However, I think our algorithm and this structure can be applied online by training online. So. Yeah. I think we can. I think I can apply this method to online directly. Yeah.
Okay. Great. Yeah. Okay. Thank you so much, Xu. That's our first talk. So our next talk is going to be given by Liu Yang from the Hong Kong University of Science and Technology. So Liu, can you share your slides and begin your presentation? Okay.
Can you see that?
Yes, we can see it. Yeah, please start.
Hi, everyone. Happy to talk with you guys. In today's presentation, I will introduce our work, Clustering Explorer Bandit for Online Recommendation System. And my presentation can be divided into 3 parts. In the first 2 parts, I will briefly explain online recommendation and its problem and talk about the existing solutions using Bandits. Then in the last part, I will mainly introduce our new Bandit policy, its experiments and regret analysis. And online recommendation system is one of the most popular application areas of machine learning. It customizes personalized recommendation services like articles, music, or short videos for each user. The system receives feedback such as clicks, comments, and likes from users, and the target is to accurately dig out the interests of users from their behavior data. Thus, recommendation system could show them the desired item to make a profit. However, traditional recommendation system always suffers from the exploitation and exploration dilemma. In the absence of exploration, supervised learning algorithms tend to get stuck in suboptimal solutions. Bandit is a classic approach for solving the dilemma. It describes such a situation. In the casinos, there are a lot of slot machines with different probabilities of winning. How to play for the most money? Should I always pull the arm of the known most profitable machines, or should I try new machines? The recommendation scenarios is just the same. Should I always recommend the most popular articles to users, or should I try to push new articles? And the target is to obtain the highest long-term rewards. The contextual bandit algorithm has been popular to solve this problem. In a contextual bandit setting of online recommendation system, articles and their corresponding features like title, category are observed by the agent. At each step, the agent chooses one article to present to users according to the click history. And the agent tries to know about user interest from the received finite and noisy rewards. Therefore, the learned parameters contain uncertainties. Taking those uncertainties into consideration, the contextual bandit prefers the known items with higher CTR, which is the exploitation. In the meantime, the contextual bandit policies also tend to choose the atoms with large uncertainties, which is the exploration. However, contextual bandit algorithms suffer from cold start problem facing insufficient data. Thus, to alleviate this problem, class of bandit policies have been studied for the last few years. In these algorithms, each user maintains a separate set of parameters, and users are divided into different groups using clustering techniques. They incorporate collaborative filtering effects into Bandit methods for enhancing performance. In the view of transfer learning, collaborative filtering shares knowledge among similar users and atoms. However, this algorithm introduces another kind of uncertainty, which is the uncertainty of clustering, and they all ignore this uncertainty. And our proposed clustering explorer Bandit, collects Bandit, consider both the uncertain estimation of user interest and the uncertain user clustering. On the one hand, collects Bandit estimates user clustering more accurately and with less uncertainty via explorable clustering. On the other hand, collects Bandit also exploits and explores user interest by sharing information within and among user clusters. In summary, collects Bandit explores knowledge transfer and further is the inference about user interest. And the detailed problem setting is, suppose there are n users, and at each time step t of the online recommendation, the agents face one user, and it's arms with context. And the agent chooses one article to recommend and obtain the feedback of the article. And the objective is to select proper actions and to minimize the cumulative regret. Our methods can be explained in two parts. The first part is the knowledge sharing via adaptive clustering. We hold the linear assumption for each user. X is the features of arms, theta is a linear parameter, eta is a Gaussian noise, and there are several interest clusters. One user's parameter vector can be a linear combination of several interest parameter vectors of clusters. The capitalized theta is generated by stacking the user parameter vectors, and L stands for the d-dimensional parameter vectors of interest clusters, and S represents the proportions of user holding this interest. Also, we assume S is sparse, which means users' interests do not cover all aspects. The sparsity property can be achieved by adding extra priors on S. And the second part of our approach is learning user interest via exploring clustering. We follow the Thompson sampling solution to fortify the adaptive clustering with exploration. At every step T, we sample tilde L and tilde S from the corresponding prior distribution, whose means and covariances can be calculated via alternatively fixing S and L. After we get the tilde L and tilde S, we could give a prediction for each arm. The arm which gives the largest prediction will be chosen to recommend. And our experiments utilize the replay offline evaluation methods, which construct the data streams from the log data of online random policy. We compare our model with 5 baselines, collects Bandit dance, cab, SCLAB, linear Thompson sampling local, and linear Thompson global. And besides, we have a warm start period in the beginning. Collects Bandit and collects Bandit dance will degenerate into linear Thompson local. And in this period, then they utilize SVD for initialization after the data accumulation. And first, we conduct the synthetic experiments where the data is created conforming to our assumption. In the left figure, we plot the cumulative regret with regard to the number of steps. Collects Bandit outperforms all the other algorithms on synthetic data. The reason is that Collects Bandit fits our assumption perfectly. However, the other 5 baseline models violate the assumption more or less. The right figure illustrates the sparsity pattern of S that is acquired under different degrees of exploration. We could see that the more we explore, the more accurate sparsity pattern we could capture. And another 2 observations in the synthetic experiment are, first, the model will converge fast if the true number of user clusters is small. And if and second is if there exists no specific pattern behind the data, collected bandit could stay very close to collected bandit dance, but still inferior to it, because collected bandit spends extra effort on exploring the sparse parameter structure at the beginning. We also conduct experiments on industry data. The last FM data is a public data set, and WeChat data is obtained from the online recommendation services in WeChat Tencent, China. As we can see, our approach, collected bandit, also outperforms the baseline model in the long run because the additional exploration of user clustering. And at last, we provide the regression analysis. The core is proof that the prediction is concentrated around the respective mean. Since it's a not jointly convex problem if we optimize L and S together, therefore we investigate by solving them separately. According to the theorem, collected bandit enjoys the same order of sublinear regret as linear Thompson sampling. One important reason is that collected bandit needs to explore smaller parameter space compared with the baseline models. And that's all. Thanks for watching.
Okay, thank you, Liu, for the talk. So we are waiting for more questions from the audiences. But before that, I have some questions regarding, for example, can you say more about how did you construct the synthetic data for the evaluation? For example, what was the assumption used to develop the synthetic data sets?
Okay. The assumption is that the parameter of interest can be generated by L and S. L and S is the parameter behind the data. We create the data according to our assumption.
Okay.
The assumption is that the data can be divided into L and S is sparse according to our assumption. We use this assumption to create the data and the features, and use the offline replay of offline evaluation to construct the stream data for our evaluation of the binary problem of different of our algorithm and the baseline models.
Okay. Thank you. So how did what was the performance of the method on, for example, some traditional recommendation measures, for example, NDCG or precision or something like that? I see the results on cumulative reward is perfect. It's very good. So what about the performance on some traditional reward recommendation measures like NDCG or something like that?
Since it's not a classification problem, it's a regression problem. We could see we could use IMSE to evaluate, but in the Bandit problem, we always use the cumulative regret to evaluate our methods. So
okay, thank you. So for our audiences, if you have any more questions, so please feel free to contact with our presenter Liu for further discussions. Okay. So thank you, Liu, very much for your presentation. Okay. So let's move to our third talk, which is still going to be given by Xu from Nanyang Technological University. So Xu, can you share your screen again?
Okay.
Yeah.
Can you see it?
Yes. Yeah, you can start.
Okay. Hello everyone, it's me again. So for the beginning, I'd like to thank my co-authors. This paper is a joint work of Technological University and the Alibaba Group. So the title is Contextual User Browsing Bandits for Large-Scale Online Mobile Recommendation. We consider the recommendation task in mobile devices. When a user opens the page, algorithm select a list of items to show in this scenario. Due to the limited screen size, like in this figure, users can only see 2 items in the screen, and they need to slide the screen to browse more items. So in this process, some items are actually not being viewed by the user. Consider a simple example shown in the figure. A user clicks the first item and then close the app. Then the items below the second one are not viewed by the users. And for the second item, we are not sure if the user noticed it or not. However, although the user doesn't click items below the second one, they are all labeled as negative samples in our dataset, and this phenomenon is very popular. So in our work, we model the recommendation task as a contextual bandit problem. Recommended items and clicks, arms, and payoff in bandit problems. The algorithm needs to recommend items to users and get feedback from users. There are many two challenges as we mentioned in the example. The first is position bias, that higher positions lead to more clicks for the same item. We call another challenge shadow exposure, which means that we do not know exactly whether recommended items are viewed or not. Items that are not viewed shouldn't be labeled as negative samples directly. In the pie graph, we can see that only 6.2% of clicks are at the last position, which suggests that only for this data, we know that users viewed all items. This shadow exposure issue affects most of the data. Our work follows the setting of a combinatorial bandit problem, where a set of items are put in each round rather than only one item. There are some works that apply different click models in this setting. However, they either ignore the influence of positions or fail to use context. Moreover, they do not consider the shadow exposure issue. So our contributions are fourfold. First, we apply a new click model considering position bias and shadow exposure issue. Second, we use context to improve scalability. Then we provide a theoretical analysis for our proposed algorithm. We also conduct both offline and online experiment based on Taobao, which is one of the largest e-commerce platforms in the world. So we first introduced the UBM model. In the above-mentioned process, we consider what can be used to address the two challenges. For each record that including all the recommended items and clicks, we know the positions of items and the clicked items. Thus, we can use this information to estimate the influence of position bias and shadow exposure issue. We use the user browsing model to estimate the examination of users, which is a probability that an item is viewed by a user. So the UBM assumes that examination depends on position and the distance to the last click. We use W to represent the examination. The subscribe K and K prime indicates the position of an item and the last click. For example, if a user clicks the first item, the probability that he views the second one is larger than the third one. This is an intuition of this model. Then we combine the UBM with LinUCB, which is a popular bandit algorithm. So our algorithm has 4 key parts: select parameter, compute upper confidence bound, and select items, and then update the parameter. So LinUCB uses the upper confidence bound to estimate the attractiveness of an item, which is mean plus standard deviation. To obtain the estimate of the mean and the deviation, we use an online version of ridge regression, whose objective is to minimize the loss function, which is a MSE loss plus a regularization loss. So to select the best parameter and the optimal recommended set, we do the theoretical analysis. Similar to previous works, the objective is to minimize the regret, which is a gap between the rewards of the optimal site and the sites selected by the algorithm. The reward function is the probability that users click at least one item. We first prove that given a list of items, the order that maximize the reward is to rank items according to the attractiveness from high to low. And we also use this lemma to select items. And in the theory one, we prove the sublinear upper bound of our algorithm and indicate how to choose ARF to achieve this sublinear bound. So we use this value in our algorithm. We implement offline experiment based on two data sets, a public data set, index data set, and a data set obtained from Taobao. We first proposed an unbiased estimator to remove bias based on assumption of UBM. The idea is to use the examination probability to estimate the true probability of clicking by using the inverse propensity scoring. Following previous works, we assume that W only depends on the page structures, which not changes in a long period. Thus, we can compute W by historical data. For features of items, we use SVD to decompose the user website metrics to get context for the index dataset, since this dataset do not include features of items. For the Taobao dataset, we built an autoencoder to reduce the dimension of the original feature from 56 to 10, because the computation complexity and the bound is related to the dimension. For the baseline, we compare with other click models used in previous works. The offline task is to re-rank historical data, which is selecting K items from 20 and 12 candidates from index and Taobao dataset, respectively. We use two metrics in the experiment. The first is the probability that users click at least one item, and the second one is the sum of clicks. The results of two data sets are shown here. We change the number of recommended items, K, from 3 to 6. The algorithms that do not use any click model performance worse with the increase of K. And our algorithm outperforms other baselines, especially when K is large. We also implement experiments based on the real-world testbed in Taobao. We use the A/B test where users entering our scenario will be randomly divided to different algorithms, and each algorithm need to select 12 items from about 40,000 candidate items for millions of users per day. The flow of our online experiment is shown in this figure. Each algorithm will update based on real-time logs. The parameters are stored in the online key-value system and used to rank items when user enters. The results of a 3-day experiment are shown in the figure below. The first figure is the change of CTR over time, and the second one is total CTRs each day. So in summary, we first model online recommendation as contextual combinatorial bandit problem. Then we combine UBM with contextual bandit algorithm and propose a novel algorithm, UBM Lin UCB. We also prove a sublinear expected cumulative regret bound for our algorithm. Additionally, we conduct both online and offline experiments to evaluate our algorithm. So that's all. Thank you.
Okay, thank you, Shi, for the talk. So again, to our audiences, if you have any question, so please feel free to post in the whole application interface. So here's one question. Can you talk more about the difference between the two CTR measures, the CTR set and the CTR sum?
Okay.
Yeah, measures.
Okay. So the first one, the CTR set, is the worst case of the CTR sum. I think it means that we don't want user to leave our scenario without click any items. So we use this matrix. This matrix is a CTR set is one if a user click at least one items. But we also want users to click more items, not just one. So we also use the CTR sum, which is sum of the clicks of a user when he leaves leave our scenario. For example, if we have 5 items and the users click 0, then the CTR set and CTR sum are both 0. If he clicks 2 items, the CTR set is 1 and the CTR sum is 2.
Okay.
So we want to use these two metrics to show the performance of our algorithm more clearly. Yeah. Thank you.
Okay. Yeah. So another question from audience. So it's a little bit long, so I'm going to read it. How do you deal with variance in the offline experiment? Seems like re-ranking thousands of atoms would lead to some very low propensity scores for recommenders that are much different from a historical policy.
Yeah. As I mentioned in the slides, we actually use this inverse propensity scoring. Since our data, we only use the data with clicks. So for the items in for the items in our dataset, most of them has clicks from users. That's the W data is not 0 in our dataset. For more detail, you can check our paper. We have a detailed explanation of how to compute W data and the W rank. But intuitively, the W data is not 0, and then our algorithm will re-rank them. So the rank of each items are different from the data. So the subscript of the W is changed to the position to the number, to the number in the recommended set of our algorithm. So in this way, we can remove the bias from data and make sure that the estimate is unbiased. But this based on some assumptions, which is also stated in our paper. If you are interested, please check the paper for more detail. Thanks. Yeah.
Oh, my apologies. I did not see that you had disconnected. 1 second and allow me to get to our next step. Very good. Well, happy to step in as we need to. And our next presentation will be given by Mololo Amiko. And I invite you to unmute, to share your screen, and to take it away.
Okay. Can you see my screen?
Yes, we can.
All right. Get this set up. Okay. Hi, everyone. I'm very happy to be here to present to you our work on offline contextual multi-arm bandits for mobile health interventions, a case study on emotion regulations. So my name is Maololo Ameko, and this is joint work with our collaborators in the Department of Psychology at the University of Virginia. So you may ask yourself, what is emotion regulation? So I'll start by defining what emotion regulation and why we care about emotion regulation. So one of the popularly, accepted definition for emotion regulation is the process by which individuals influence the emotions they experience and when they experience them, and also how they experience them. And so some of the examples of how people regulate their emotions from day to day is, perhaps, eating a lot, which is called emotional eating, doing some fun activity outside, and maybe, binge watching a lot of funny videos to make yourself feel better, or, even listening to sad music online. You may ask yourself, why do we care about emotion regulation? It turns out that, in psychology, it's known that flexibly applying different emotion regulation strategies in different contexts is associated with psychological well-being. And so clinical psychologists are very, very interested in, ways in which they can make users, they can help users to regulate their emotions by deploying technologies that will allow them to choose the right emotion regulation strategies at the right time in the right context. And so, we also know that, the effectiveness of emotion regulation strategies vary by context. And so if we are able to build, an algorithm that is able to recommend the right emotion regulation strategies, we can easily scale them to, to users or to patients through smart devices. So in this work, we aim to develop an algorithm that recommends emotion regulation strategies that will be effective for any user person in a given context. And so how do we do that? We already have some data, where from a study where, there were about 114 socially anxious participants aged between 18 and 45. And the study was conducted over a study period of 5 weeks, where each participant had an application installed on their phones where we can stream different kinds of data. One of the data sources are named active data, where, which is basically we send prompts to users 6 times in a day, where they respond to a survey, and which is an example right here. And another source of data is passive data from your phones, so the sensors of your phone, the GPS, the accelerometer, and maybe even activities. So what you are actually doing, whether you are cycling, driving, or any such thing. So we model the entire process of emotion regulation as a sequential decision-making problem, and we use a modeling framework called the Contextual Bandits, which everybody in this RecSys community is familiar with. So basically, the idea here is for us to learn an initial policy, which we can then test out in the wild, because always there's that risk of not being able to recommend the right, and sometimes it's even unethical to do that in a healthcare setting. And so for us, it's important for us to use offline or historical data to learn that initial policy and confirm it in another study. So of course, given that we are using a contextual bandit, we define different aspects of the contextual bandit. So the state, for example, we have some of the examples of variables that are in our state space are whether the person is at home, at work, whether the social context of the person, whether the person is with friends or family, or what activity the person is doing. So some of the actions in the action space are basically emotion regulation strategies that are accepted in the literature as adaptive strategies. What I mean by adaptive is that basically strategies that are recommendable or are right to recommend. And so, some of the examples of that is seeking advice or comfort from others, eating food, accepting the feelings, or coming up with ideas or plans for actions, to take actions. And the reward function is basically a binary vector, below and above the perceived effectiveness. The perceived effectiveness is basically, what the person, the user reports to us as the effectiveness of the strategy he has used. And so to do the learning, we explored different estimators. There are a lot of estimators, offline estimators that are in the literature, and so we explored all of them because there's not any one of them that is guaranteed a priori to work on our data sets. And so some of the examples are the direct method, the inverse propensity weighting method, and the doubly robust method. And so each of them have their own advantages and disadvantages. And the direct method, for example, has very low variance but very high bias because of the model that you are using. And the inverse propensity weighting has a very high variance, due to, as the previous speaker might have mentioned, due to the possibility of there being very low propensity scores in the denominator. And there is variance of inverse propensity weighting called a trimmed inverse propensity weighting, where you can sort of cap off the low propensity weights with a threshold called a tau, or the trim variable. And then there is the doubly robust method, which is a consistent estimator, but balances between the variance and the bias. So we benchmark our approaches against the random and then the observed behavior. So it was the random is basically you selecting at random any strategy at all, and the observe is basically what a person is already doing, and so we want to be able to make sure that whatever algorithm that we propose is better than the observe or what the people are already doing before we deploy them. And so some of the analysis choices that we've made in this work is we use logistic regression as a value function approximator. We use the propensity score. We estimated the propensity scores from historical data using the generalized boosted model as one method that is known to be generally more robust to learn propensity scores when you don't have the behavior policy. And we perform a 5-fold cross-validation for policy evaluation. So these are some of the results that from our analysis. We report the cumulated the mean reward across different algorithms on the in each column. Doubly robust, the direct method, the offset tree. The offset tree is the method that is which is dependent on the inverse propensity weighting, and then the observed and the random. And we evaluate them using the trimmed inverse propensity weighting. So what we observe here is that the doubly robust method performs better than all the competitors and significantly better than the baseline approaches like the observed and the random. So that is, we choose the doubly robust, but the clinicians typically are interested in knowing for what analysis, what research questions that analysis can kind of inspire for future studies. And so with the approaches that we've taken, we can sort of observe what are the features that are most impactful in determining the effectiveness of strategies. So we, from the analysis, we found that the timing, the appropriateness of the timing is very important. And, the activity the person is actually doing is also very important. And the motivation of the person to change his feelings is also very important. So these are some of the observations, qualitative observations that we've made from the data analysis. So what are some of the limitations of this work and future directions? In terms of limitations, we assume that all the confounders are observed while we were estimating the propensity scores, which is almost always not true in the observational setting. And we also assume that there is enough overlap. The policy that we've learned currently, optimizes for short-term immediate effects, but there is a sense in which the strategies that people are using may have long-term effects on their outcomes. We also approximated the propensity scores just by the limitations of the data. And ideally, we would like to be able to know what exactly the behavior policy is that people are using, but we don't have that. So it's approximated. So some of the errors might be propagated in the results. And for future directions, we intend to model at real time the affective states for a more accurate state representation of the person. And we want to develop approaches that are robust to unobserved confounders. In summary, emotion regulation strategies, effectiveness is context dependent, and we've learned an initial policy and evaluated them with log mobile data using contextual bandits. Thank you.
Okay, thank you so much, Malolo, for your nice presentation. So for our audiences, if you have any question, you can just feel free to post in the OWA chat box. So you mentioned co-founders. What are possible co-founders can we imagine in this problem? Can you give some examples about possible co-founders for the problem?
Yeah, definitely. So for example, we are looking at we are trying to model how people make choices. Yes. And it's actually very hard to imagine the number of confounders, but one of the confounders that are likely to happen in this work is the energy of the person. What the energy of the person is, we have whether the person is able or not to choose the action. And so that particular confounder may have an effect on the choice of the treatment, and obviously they have an effect on the outcome that we observe. So that is an example of confounder.
Okay.
Yeah.
Okay, great. Yeah. So maybe another question for how did we get the in that figure? So we have a few dots. Yeah, this figure. How do we get the categories in the y-axis of this figure? How do we have this?
Yeah. So basically, these are the effect sizes of. So we use the linear regression, and basically these are the effect sizes, the absolute effect sizes of each of the.
Oh, okay.
The features that's going to our state space.
Okay, great. So if our audiences have other questions, you can communicate with our presenter directly for the questions. Okay, so thank you so much, Manolo, for the presentation. Okay. So now let's move to our final presentation, which is going to be given by Ramanathan from SBX Technology Corporation, Japan. Ramanathan, can you share your screen?
Yeah, 1 second.
Okay.
Can you see it now?
Yeah, we can see it. Yeah. Yeah, you can start.
Okay, hi everyone. 1 second, I'm not able to see this. Okay, yeah. Hi everyone. Today I'll be talking about a recent project we worked on, building a reciprocal recommender system from scratch, and I'll be sharing the learnings from our process. This is joint work between SBX and Matching Agent. My name is Ram, and I'm from SBX Tokyo. Tapple is one of the leading dating applications in Japan that connects young people by their hobbies and interests. Started service in May 2014. Tapple has over 5 million registered members. Until date, Tapple has made over 200 million successful matches, which is the largest in the Japanese market. So once inside the app, people are shown profiles of the opposite gender, which they can swipe left to like and right to pass. And when two users like each other, it's a match, and matched users can start a conversation by exchanging messages. Our goal here is to maximize the potential for mutual likes or matches. So designing a recommendation system for such a large-scale online dating app is complex and challenging for a number of reasons. First, as you might have seen here, recommending people is not just unidirectional. It's equally important to recommend other target users who would reciprocate the subject user's interests. Second, people are dynamic. Consider this scenario play out between three people, Shun, Manami, and Saki. Initially, Shun is first recommended Manami, but for some reason, when Shun likes Manami, Manami decides to pass Shun. Depending on this feedback, Shun broadens his preferences and likes Saki, who likes back, and it's a match. The user's as you can see here, the user's preferences evolve over time. It could also turn out the other way. If a user receives more positive responses for their likes, the preferences might become more selective. Third, we observe that the interaction network is sparse and users are very selective about their preferences. Hence, in addition to solving the information overload problem, our reciprocal recommender systems here should be careful not to overload the users with poor recommendations, as rejection directly impacts user retention for the app. So for modeling the mutual preferences, we start from a data-first approach. In conventional dating apps, people usually look for that one single match and we are done. But in our setting, we observed a significantly high number of matches per user. What you see here on the right is a scatter plot which shows the distribution of matches per user, where the x-axis shows the number of matches in log scale, y-axis shows the number of users in log scale, and each point on the scatter plot shows counts of matches per user. This distribution shows most users have a significantly high number of matches. So we wanted to build on this insight to develop models that learn useful embeddings of people that exploits the match information. So we first clean the data set to remove users with missing or invalid data and filter users who are active in the last n days or n weeks. We have the interaction data and the user profile metadata that has information like location, users' interests, and so on. And for training our models, our framework has all the usual collaborative filtering algorithms that we have discussed in this conference so far, be it matrix factorization, learning to rank, and neural network-based methods to generate the top K recommendations. I'm not going to go into the technicalities and the math behind the models here. The idea is to show the process and the impact. We used match interactions as positive samples and interactions where one of the users passed as negative samples. And for inference, for a given user, we compute their preference vector based on their past matches. And once this is done, we retrieve nearest neighbors using an approximate nearest neighbors algorithm that runs and gives recommendations in sublinear query time. We note that the quality of our embeddings and in turn the recommendations is not sensitive to the choice of the approximate nearest neighbors algorithm here. And for new users, we generate a pseudo embedding from the embeddings of users who have similar metadata as the new user. But then we found not all users had enough matches to model their preferences with high quality. So on the other hand, even though unidirectional in nature, likes contain a richer fine-level representation of users' preferences. This meant we had to deal with 100x larger training set in terms of the number of interactions. There was this interesting paper from last year's RecSys along this idea, which is basically to learn the unidirectional preferences from males to females and females to males separately, and then use some kind of an aggregation function to derive the reciprocal preferences. We adopted this approach to fuse our unidirectional preferences learned from the males to females and females to males and which is basically from the likes, and share the results from this approach in the slide here. So for offline evaluation, we use standard matrices like precision, recall, and F1 score. We take 1 month's data as training data and the subsequent 1 week's data as test data. Our method here, as you can see for the matches, gives us 27% increase in recall over the previous matches only model. But we all know offline evaluation is not representative of online performance. So we use engagement and conversion as matrices to evaluate online performance. First, for measuring the short-term objective in terms of user engagement, we basically look at the likes, which is the fraction of recommendations which convert into likes. And for the long-term objective, we look at the ratio of matches to likes. The bar graph on the right here shows the results of the online matrices. While our method improved on engagement, we still found it was not resulting in conversion of likes to matches. After analyzing the logs, we found this was due to users who were not active at serving time. So when a user liked another user, but the other user is not responding, this recommendation was basically not converting. We had to debias to balance trade-off between relevant users and recently online users. And once we fixed this with a re-ranking solution, we found a significant jump in performance. So to formalize the end-to-end setup, we adopt the classical two-stage information retrieval pipeline, where at the first candidate generation stage, we generate a few hundred good candidates, optimizing for precision. And this comes from basically starting with an initial set of thousands of users, or in fact, hundreds of thousands of users, and using collaborative filtering algorithms. And in the second stage, we do online re-ranking, optimizing for recall. And the objective here is to balance multiple objectives to recommend recently logged in users, newly registered users, and removing bias coming from recommending popular users who already have lots of likes and matches. So next, to put the system in production, as a small team, we had to overcome a number of design challenges. To overcome these, we first split every independent component in the system, be it the pre-processing, the training, the inference components, into different microservices, and build a distributed workflow so every new model we build can be easily deployed. But the pre-processing routines, training algorithms for different models, and the inference algorithms would have different environment requirements. So we use Docker to containerize each of the microservices. Next, keeping the models always online to serve recommendations would be expensive. We pre-compute the recommendations and store it in a high throughput, low latency distributed key value store, which offers read latency, which is of the order of single digit millisecond latency, like Amazon DynamoDB. So the recommendations can be retrieved in sub 100 milliseconds query time in the worst case. And for transferring the recommendations generated from the AWS instance to Amazon DynamoDB would take hours. So to tackle this, what we do is we first split the entire recommendations dataset for all the users into smaller chunks using an SQL query engine and store it in a distributed data store, and then spawn multiple Spark workers, which upload the data in parallel to DynamoDB. Finally, error handling and data access patterns have to be streamlined for each of the microservices as they become more complex. So to tackle this, we use AWS step functions, a serverless orchestrator that would trigger each step containing a microservice sequentially in an event-driven workflow. So here is the end-to-end workflow summarized in one slide. Aggregated input data, which comes in the form of likes, passes, matches, and also the user metadata, which contains all the side information, triggers our algorithms. And these algorithms retrain the user's embeddings periodically. So for warm start users already in the system, a batch job generates top K recommendations and spawns multiple Spark processes that copy the recommendations from the cloud storage into the Amazon DynamoDB, which is the distributed key value store here. For cold start users, we have an always-on instance with the model artifacts that serves as a streaming endpoint. For every new user, we create a pseudo embedding for them and generate recommendations. By using AWS and its serverless infrastructure, we were able to build this with significant time and cost savings. So to summarize the key learnings of our approach, we realize making recommendations solely based on past interactions is not enough. By balancing trade-off between relevance and recommending potential partners who are recently active online and new users, we could get better results for our users. Users' preferences change with every interaction they have with the recommendation system based on the feedback they receive, and it's important to update the embeddings and recalibrate model parameters frequently. And finally, containerizing algorithms into microservices and orchestrating them into an event-driven workflow goes a long way in scaling our models. Finally, I would like to thank our collaborators here, and thanks for listening to the talk. Any questions, please?
Okay, thank you so much, Ramana sir, for your presentation. So to our audiences, if we have any questions, so please feel free to post in the OWA chat box. So one question. So I think that mutual preference learning is a very interesting task. So could it possible? Is there any other scenario that can this framework be generalized to any other recommendation scenarios that you can think of? For example, that I can use this mutual preference learning
Sure.
framework.
The most obvious application studied in literature is online dating, but there are real applications which need reciprocal recommendations in terms of job recommendations, where the interest of both the employer and the employees is very important to build a strong reciprocal recommendation system. It's also an interesting setting for social networks where people, it's not just important, like in case of Twitter, it's mostly unidirectional, where people, if you follow one person, the follow back is equally important. But in a more general setting where the other parties' preference is also important in social media networks, reciprocal recommenders are an interesting field of study. But for whatever reason, it's been an underappreciated field so far, and it's been largely overlooked. But recently, there's been increasing interest in this setting.
Okay, yeah, great, yeah. So another question from our audience is: do you remove bot users in data sets, and if so, how? So I'm afraid that many bot users skew the result of the data.
Sure, this is one of the important problems we faced initially. So a lot of users would have birthday data or registration data, which is obviously invalid, which you can filter out based on the pre-processing routine you have. So at the time of pre-processing, you basically filter out these data points which have data points which are largely divergent from the distribution you see in the usual data. And the other thing is users who have exorbitantly high number of interactions, which could also be bots or from the images. These could also be studied to remove spurious data points.
Okay, yeah, okay. Another question. So if user A chooses like to user B, is that action sent to user B? So this might affect their subsequent choices of user B.
So yes. Traditionally, in dating systems, there are both kinds of systems where both sides are double blind, where user A's interaction to like to user B is unknown until the point user B also likes user A. In our setting, though, user A, if A chooses to like B, the action is indeed sent as notification to user B, and the user B likes back. So this, as we showed in the initial slide, this has a very important impact on the user's preferences changing over time. But in our setting, we observed that this could lead to people being more sympathetic if they could change their preferences over time. Initially, they would have an initial preconceived notion of preferences, but based on the interactions they receive, they could receive another set of users who have another specific set of preferences, and this is definitely an interesting field of work to study.
Okay, yeah, okay. So we still have a few minutes, and so let's take a look at another question. So, how do you define active users in this work?
So yeah, here the active users, it depends on the business case. So it could be recently active in terms of days, hours, or weeks, depending on the question we have. So it also depends on the modeling problem we have and the system in production. It's basically you need to try different settings and come up with recently active users, but I cannot comment on what's in the production right now.
Okay, yeah. And yet another, have you compared the result of your method, for example, in terms of conversion and engagement, with a pure last online ranking algorithm, given your re-ranking based on last online time?
So currently, the results we show here are based on offline evaluations. For online evaluations, whenever we want to compare purely based on online last online time, we would need to look into online evaluations. So for that, we are still looking into ways to study, compare different methods based on online, purely based on online networks. But generally, we find that from offline evaluation that modeling users' preferences based on past data has a significant impact over purely online users, just from offline evaluation setting based on average recall and so on.
Okay, thank you. So maybe the last question, because we are almost we have almost used up the time. So how is the trade-off between preference score and the recent activeness controlled in your setting?
So this at the online point, you could use a number of methods. It could come from a simple linear model which weights the different parameters you want to model in terms of popularity, in terms of recently online and new users, to come up with a re-ranked score based on a linear model which weights different parameters differently depending on the heuristics you want to operate. This could also be tuned based on rule-based heuristics, which you could have. You can try different methods. We basically look at different methods which work and tune it accordingly.
Okay, thank you. So it seems that this work generated a lot of interest from our audiences because there are a lot of questions coming. But because we have run over our time, so if our audience have more questions, so please feel free to contact with our presenter, presenter, directly to communicate offline. Okay. So thank you everybody for joining this section, and thank you to all of our speakers for presenting their nice work. So. So just a reminder that please submit your, just a reminder that please check out our social activities over the next hour before the next session starts. Okay. So thank you very much for joining this session, and we look forward to seeing you again in the following sessions of this conference. Okay. Thank you, everybody.